Hello, my name is Jacob LaFontaine. I'm a research hydrologist with the South Atlantic Water Science Center of USGS. Today I'm going to give you a presentation as part of the Georgia Water Resources Conference on the USGS National Hydrologic Model, continental scale modeling for decision-making, research, and education at local, regional, and national scales. I just want to give you an overview of the presentation today. The motivation for developing the National Hydrologic Model infrastructure, give you a description of the NHM infrastructure, some past and current applications of how it's being used within USGS, and then the availability of the National Hydrologic Model for new applications and also educational or training purposes. So our motivation for developing the NHM infrastructure, there's some overarching research objectives in hydrology that we have as USGS scientists, providing useful hydrologic information to resource managers. We see that from USGS, folks are probably very familiar with the National Water Information System, or NWIS, going to USGS websites, looking at current or past streamflow conditions. The images on the right side of the slide show for a time in the summer in June on top, and on the bottom in February, this most recent February 18th, and looking at the active stream gauges and how they rank compared to their historical flows for this time of year. So now where we have a lot of data collection sites, we also look to couple that with modeling efforts within the water mission area. Another goal is improving the understanding of the hydrologic system. So as we develop models, looking at what we're able to represent, which pieces we're perhaps not capturing, and are there opportunities to improve our representation of those pieces of the hydrologic cycle, and improve the simulation tools and applications as we see opportunities for advancement in process representation. How does that actually feed into the tools that we use and the model applications we develop? Additional motivations, so when we look historically, different types of information that are available, say from a stream flow perspective. So this image on the right is from a report from 2013 by Julie Kiang and others within USGS. And out of this Gauges 2 data set that James Falcone developed in 2010, classifying various stream gauges across the country as reference or non-reference in respect to the amount of disturbance perhaps in a watershed, flow regulation, water use, those types of things to classify the watersheds. And so when we look at this image for the Southeast United States, those bluish areas are the watersheds that are encompassed by the reference gauge network. And so we see that there's a lot of white area that may either not have a stream gauge to collecting data in it, or those are areas that we have non-reference streamflow information where there's some kind of impacts to the flow record. And so needing methodologies to provide water availability in ungauged watersheds or during ungauged time periods, as with the stream gauging network that USGS currently maintains. We have stream gauges that will operate for a certain amount of time and then will be discontinued, and others can pick up in different places. So using models to fill both spatially as well as temporally, and how we do that across the country. In addition, when we look at how our modeling has developed in recent years, typically watershed models have been developed for, say, a smaller watershed that perhaps has a streamflow gauge at the outlet, and so you're just looking at that response at that one point. But as computational power has increased and looking at available data sets to parameterize models, we've now expanded the spatial extent of models to from basin to region to national scales, and at varying resolutions. And so figuring how we now can run these models, the simulations, how can we calibrate these in a consistent way for a national scale application as opposed to a localized watershed. And building off the lessons learned in past studies, one big study that had lasted at least a decade, the Prediction Ungaged Basins study. So when we start to look at what information we have available, what information we may need to represent the water budget, stream flow information, various parts of the hydrologic cycle, across the country, we see the need for a nationally consistent framework that can look to answer questions about water availability, changes in timing and source of stream flow, as perhaps you have changes in climatic regime or in land cover characteristics. Being able to characterize uncertainty. So just because we have a time series of stream flow, whether it be measured or simulated, what is the range of uncertainty around that data point to give those that use the results an idea, of how confident we are in those estimates. Assessing climate and potential climate and land cover change effects, and how we can look at different scenarios based on what has happened in the past and what could happen in the future. And again, having the flexibility to look at perhaps a localized watershed or a regional effort or at the entire nation at one time. So I'll give you a description of the National Hydrologic Model Infrastructure as it stands today. So the NHM is made up of three primary components. So we have the physical, the modeling codes for the physical models. We currently have a daily time step and a monthly time step model. The underlying geospatial fabric of modeling units, so polygons that represent the landscape and then connected to stream segments to represent the stream and river network, and associated parameters, model parameters with those modeling units. And then looking at the model input data of weather, climate that would force the model simulations. So estimates of precipitation and air temperature are the popular ones that are used to drive models of this type. And so this, the NHM infrastructure has some associated publications, both the journal article and the USGS publication that are available to give further description. So to look at the physical models that are currently in the NHM infrastructure, so we have the monthly water balance model, which is based off the Thornthwaite water balance model, so a simpler parameterization, not a lot of parameters, and operates at a monthly time step. And then we have the daily time step precipitation runoff modeling system. So this is a modular, deterministic, distributed parameter physical process-based model. And so in the schematic for PRMS, each of those boxes represents different modules that have various options to simulate the hydrologic cycle, from incoming precipitation and air temperature and solar radiation, how those climatic forcings interact with plant canopy, build snowpack, look at infiltration and movement of water across the landscape, as well as through the soil profile into the groundwater reservoir. And one thing to note is that recently the release version of PRMS, we do have a stream temperature module that's based off of the SNTemp stream network temperature model to simulate daily mean stream temperature. Looking at the geospatial fabric, so in developing these model units, not starting where in the past we may start from a digital elevation model and then look at various points of interest and then build up our modeling units from that DEM. Now we've gone to aggregating existing data sets such as the National Hydrography Dataset Plus, so NHD Plus. So at the time that we first developed the geospatial fabric, NHD Plus version 1 was the stable version. Version 2 was still being worked on. And so this, by aggregating up the NHD Plus catchments and flow lines, are their terminology where we work with hydrologic response units and stream segments. And so aggregating up their more than 2 million catchments into about 110,000 hydrologic response units that are then connected to about 55,000 stream segments across the country is this version 1 of the NHD, of the National Hydrologic Model Geospatial Fabric. And so that was published back in 2014. Several model applications of PRMS and monthly water balance model have been applied to that version. A year ago, we did an update called version 1.1, where we did not have modeling units discretized at the same resolution across the Canadian border. Our spatial team was able to use the NHD high-res data sets to then expand our modeling structure past the Canadian border to give model units of similar scale. So looking at, the Columbia River, primarily in the northwestern US, being able to then simulate those hydrologic simulations into across the border and back. Currently, there's a version 2.0 that's being worked on, and that is now using NHD plus version 2. So there's some additional data sets associated with NHD plus version 2, and that one of the things is actually lining up with HUC 12 pour points. So a lot of our reporting out has been at HUC 12 spatial units, but the model doesn't run on the HUC 12s, and so having that crosswalk embedded within HD plus version 2 will be a big help. When we look at climatic forcings, so we have some historical versions of historical forcings, and then also potential future based off downscaled general circulation models. So here is a list of the historical products that we have downloaded, processed to the modeling units. So there's a couple different versions of DayMet, which is, these are all daily time step and they're all gridded products of varying spatial resolutions. So DayMet is a 1 kilometer resolution for the recent past. GridMet is a 4 kilometer version that we're currently using and it actually updates until yesterday. So where DayMet updates the previous year, usually within 6 months into the next year. Then there's a couple other longer term data sets, the LIBNA and the Mauer that we typically use for climate change studies is at 12 kilometers. And then we also looked at stage 4 radar. So all of these have been, with a spatial weighting overlay, have been transferred to the modeling units of the NHM. Some of these also downscaled GCMs have been processed so that we could look at potential changes or effects on hydraulic response given climate change scenarios. And so these are out of the CMIP 5, the coupled model intercomparison project version 5. So there are several models here with varying coverage of the RCPs, the representative concentration pathways. So looking at some applications out of the NHM over the past 6 to 7 years as we've developed these tools. So one for our region is that we used, where the NHM has been developed for the conterminous United States, we have software that enables us to extract subbasins from the national model. And so for this latest application that was published in 2017, looking in the Apalachicola, Chattahoochee, Flint River Basin, we were able to take that extraction of the ACF to do a water availability analysis in that basin. So this is part of the USGS National Water Census, which started off with the Secure Water Act in 2009. So looking at water availability from 1982 to 2012, there was a loose coupling with a ModFlow groundwater model in the southern part of the basin in the Doherty Plain for 2008 to 2012 time period. And we also included monthly estimates of water use in the basin during that 2008 to 2012 time period. After working on the ACF model, then there was some work funded through the Gulf Coastal Plains and Ozarks Landscape Conservation Cooperative, as well as some funding from the Southeast Climate Adaptation Science Center that looked to take a regional extraction out of the NHM for a large piece of the southeastern US from West Texas up to Missouri and as east to the Savannah River Basin, and looking at potential effects of climate and land cover change on water availability. And so these simulations encompass the period from 1952 to 2100. the modeled units were about a fifth of the country. So where there's 110 modeling units for the country, this model was about 20,000 hydrologic response units. And out of these simulations for historical and future, there were streamflow metrics that were computed out of the daily time series that were then used by the cooperators to do follow-on studies. So looking for this to provide a foundational data set with which others could look at ecological response, species response to changes in stream flow and related hydrologic variables. And so that was published in 2019. Then looking currently what's going on in the water mission area tied to the National Water Census. So we're using the full CONUS application of the National Hydrologic Model to look at a near real-time estimate of the water budget at a HUC 12 scale, which is what the model units are at. So what this is able to do is now we've added this into a pipeline, which with the GridMet forcings, they update every day. And so we're able to go to the data source, process those forcings, run the models, and then make this storage map, which looks at water storage in the various model components across the country and how today's storage kind of ranks to this time of the year in the historical record. So are we about as much water storage as there typically is? Is it drier? Is it wetter? And so this kind of a first level prototype in the water availability product suite that USGS is looking to build upon. We're also looking at incorporating seasonal to subseasonal forecasting based off of available data sets from NOAA and how those can be used not only to look at the natural conditions or water availability from the hydrologic model, but then also couple with water use models to then provide those estimates in the future. So the tools that we're using within USGS, and also I think that could be leveraged for applications outside of USGS, or say for training educational uses. So we have different versions of the National Hydrologic Model, primarily with the precipitation runoff modeling system. So there's pre-calibration versions or versions that have been calibrated with various climate forcings. The DAMET and the Mauer based runs are currently available, and then we're also calibrating to GridMet. Model extractions are available upon request. So from the NHM infrastructure and the applications that have been developed, you can get a cutout from the NHM for a particular watershed of interest that includes the model inputs to run the model, outputs from simulations that we've previously done, as well as the accompanying GIS, the shape files of the model units to then look at post-processing or other analyses. Also, we have some training materials. So there's various USGS reports documenting the NHM infrastructure, the underlying hydrologic models or water balance models. And then we also recorded a few years ago a series of training videos that were pulled from materials that were used in the past to teach PRMS out at the National Center in Denver. And so those videos are actually available on the USGS HydroTube webpage. And so that link is provided here. And then also if there's additional information about the NHM that you'd like to see, we have a brief description on that last web link that looks at explaining the various parts of the NHM infrastructure as well as past applications of the NHM infrastructure. And so this graphic on the right represents where we have our data repositories that may get updated with new applications of the NHM, new climate forcings, and then out of that catalog, we can provide model extractions based on a particular version of the NHM with particular climate forcings for your area of interest. And so I thank you for your time and look forward to the follow-on discussion that we'll have as part of the conference. Thank you.